Thank you for attending this virtual talk. My name is Brandon Bestelmeyer. I'm the research leader at the USDA-Agricultural Research Service Jornada Experimental Range in Las Cruces, New Mexico. And I'd like to thank my co-authors listed here that are also at the Jornada. I'm going to talk about the use of big data in the broad sense for local collaborative science projects, and especially involved in land management. Although we tend to think of big data in the abstract as being incompatible with local site-specific science, I hope to illustrate some of the tools and ideas that we're working with to make this link and to be able to use big data to extend the operation of local collaborative management activities. Land management science, which is really the philosophical foundation for what we do here at the Jornada, has the objectives of conserving land potential in managed systems, including soil health, biodiversity, and ecological processes, enabling adaptation to climatic and societal change, making scientific information on diverse indicators of interest to different constituencies available in the context of communities so that they can align their decisions with desired outcomes. And we also acknowledge uncertainty in the outcomes of management decisions by monitoring what we do, adjusting on the fly when we can, and then tailoring those decisions to spatiotemporal context. Local collaborative projects are really putting into practice this philosophy. The hope is that you have interactions of stakeholders and scientists in a shared landscape where information exchange can occur, and that data can be provided to those stakeholders on a variety of meaningful indicators that can be compared among potential management strategies or individual decisions. Scaling up these kinds of collaborative adaptive management activities, however, is a problem. If I think just about USDA related programs, we have 166 land grant institutions and USDA Agricultural Research Service labs, but we have over 2 million farms in the United States. And so if we wanted to bring everybody under the umbrella of these collaborative management activities, those would be really large and unwieldy group sizes. So scaling up is going to require some new strategies, and certainly we need to train and employ more local community-based ecologists, but a number of interlinked big data related tools can be used to assist in knowledge production and knowledge use. So when we talk about big data, there's really two aspects to consider. First is the modeling of large-scale patterns by combining large data sets. A good example of this was published in Science earlier this year, in which a large data set of bumblebee records was combined based upon their spatial location with a time series of temperature to understand the influence of temperature and other variables on changes in bumblebee species richness at a very broad extent, but with fairly fine grain of information. Another use that's probably more familiar is personalized information delivery via the web or on your cell phone, based upon crowdsourced data that we inadvertently often provide to these large data sets. So these two different aspects of big data can also be applied to land management science to reduce spatial and temporal uncertainties in our scientific interpretations and management recommendations, to encourage participatory data collection, and to allow for richer interpretations of management decisions. So how do data get big, and how do we apply these big data in support of land management? The first step is to standardize indicators, and in our case, thinking about a framework that we use in rangelands, rangeland monitoring methods. Once that standardization has taken place, then you need to upscale field monitoring via training and also the use of mobile applications. So we have lots of data being gathered. We can integrate those field point data with remotely sensed data using machine learning algorithms to turn those points into a continuous surface of information that can be provided on different indicators. We then can calculate indicators. And if we're talking about vegetation and vegetation and surface cover indicators, those can be transformed into other indicators through models at the point, as well as using map data. We then interpret those indicators. We exchange knowledge. We deliver that information to the user, and the user provides monitoring data back to help change our interpretations where they're faulty. And then, of course, this is used in a cycle of adaptive management by individual landowners or as a community. So standardized methods, this is really where a lot of our ideas got their start at the Jornada, with development of the monitoring manual for grassland, shrubland, and savanna ecosystems. This is really fundamental to everything else I'm going to talk about, because it provides this common basis for modeling additional indicators, for upscaling, for creating standardized interpretation tools. Similar protocols, of course, are evident at the National Ecological Observatory Network and the US LTAR. This standardization, as I said, is fundamental. Then, of course, we have to do the hard work of upscaling these methods via training, and then, of course, this is getting easier now with mobile apps. The monitoring manual methods have been trained to hundreds of scientists and technicians throughout the world, and this has resulted in 65,000 points with standardized vegetation data across the globe. What you're seeing there, all those black points in the United States, those are all the rangeland standardized monitoring sites, and a similar interpreted map in Mongolia. You can access the data in the United States through the Landscape Data Commons website and the mobile apps that allow for these data to be gathered in a simplified way, but that are compatible with these methods at landpotential.org. Then we can link the field data to other spatial data layers to create continuous gridded data products. An example that specifically used the standardized monitoring methods is the rangeland analysis platform, which you can find at rangelands.app, developed at the University of Montana, in which they used machine learning methods trained on the standardized monitoring data with other contextual layers, including remotely sensed and other spatial data, to create continuous estimates of vegetation functional group cover across rangelands of the western United States. Then we can calculate additional indicators on top of the field or the gridded cover data. Models such as the ARO model being developed here by Nick Webb and his colleagues at the Jornada can create estimates of vulnerability to wind erosion, and similar kinds of efforts can be used to determine habitat suitability. And these models are really based on long-term experimentation and a deep history of research. So then we have to interpret those indicators via links to some kind of benchmarks in an information database. Ecological site descriptions, which I'll describe a little bit more detail in a minute, have been produced by extended peer communities, including scientists and agency managers, as well as on-the-ground land users. And they can provide for context-specific evaluations and management recommendations, because they're specific to particular soil and climate zones. So how do these ESDs work? This is a database that we built to house ecological site description information, the Ecosystem Dynamics Interpretive Tool. And the first step is to find your ecoregion, which determines your climatic potential. The next step is to find your soil type, which then gets you your climo-edaphic potential vegetation. In this case, we're at the sandy ecological site in the 8 to 10 inch precipitation zone of the Chihuahuan Desert of southern New Mexico. If you need help identifying your soil, there is a function within the LandPKS app that can help you identify your particular soil type that then is linked to a particular ecological site description. And then each ecological site has a state and transition model. And so the next step is to determine your ecological state. These tools are potentially available across the United States and of course are in different stages of development at the present time. So once you have your state transition model, you know, how do you interpret and link what you're seeing to a particular management action? For example, if I'm on the sandy ecological site and I see Bouteloua areophyta or black grama cover at 45%, mesquite Prosopis glandulosa at only 0.5, and lots of well-developed cyanobacterial crust, well, this is as good as it gets. You don't get any more cover than this that we have ever observed. Very low wind erosion potential and good habitat for grassland birds and rodents, as well as good potential for livestock production. If you see this state, however, lots of bare ground, your black grama cover is 2%. They've been replaced by other bunch grasses, Sporobolus and Aristida species as your dominant. The shrubs are becoming a little bit more dense and those crusts are gone. This has a lot of problems and potentially high wind erosion and a risk of losing all perennial grass cover due to soil erosion feedbacks. And then you may end up at this state where you've lost all your Bouteloua areophyta cover. The bunch grasses that you see are just associated with the canopies of these shrubs that are now dominant across the landscape, coexisting with large bare areas that have no crusts. This is a site that is eroding. You either learn to live with it or you hope for extreme rainfall events that might re-establish perennial grasses. In this site, killing shrubs is probably not a good idea to try to reduce competition with grasses and get your grasses back. You're just going to increase the erosion. But in the previous state, you know, getting rid of a few of those shrubs might prevent progress toward a state like this. Then you can map these kinds of interpretations across multiple ecological sites, which are shown in those primary color, and the shades are the states. This is what we call an ecological state map based upon remote sensing data. And these essentially serve as a spatially explicit management guide. Then this information can be delivered via mobile and web technologies to users that are making decisions, and those same users can contribute standardized data to monitor what the progress is in terms of sustaining a desired ecological state or creating a transition to a more desirable state. And this is really what comprises adaptive management. And our long-term goal is to design strategies to employ these multiple tools in iterative decision-making to involve more local scientists with land managers. We've built a lot of these tools. We are applying them in certain circumstances, and I think what we want to do is tailor them and upscale them throughout the United States and the world. So I hope I have convinced you that integrated big data tools in the hands of local scientists could provide more ecological information, increased utility for management, and more participation and ultimately better management decisions.